Let's take a look at the hardest AIME problem from 2011. This is problem 15 from the AIME 2. Let p of x be this polynomial. A real number x is chosen at random from this interval. And we want to find the probability that this weird thing with floors is equal. And that probability is going to be of this crazy form. And we need to find that probability basically. And so first, let's just break down what this even means right here. So we have that the floor of the square root of p of x is equal to the square root of p of the floor of x. And so this floor of x is always going to be an integer. And so that means we have that this p of the floor of x must be a perfect square because this floor is also an integer. And so if this is an integer, that means p of the floor of x has to be also a perfect square. So we have p of some integer equals a perfect square. And we have bounds on our intervals, so we can just test basically every number in this bound, and that's probably the best way to do this. So I'll save you time, but basically what you do is you find p of 5, and if you plug p of 5 in, you get 25 minus 15 minus 9. That's equal to 1, and you can just keep on going all the way until you get to 16, or all the way until you get to 15. So p of 6 equals 9, p of 7 equals 19, p of 8 equals 31, p of 9 equals 45, and we'll just keep going. P of 10 equals 61, p of 11 equals 79, p of 12 equals 99, p of 13 equals 121, p of 14 equals 145, p of 15 equals 171. We don't have to go any farther because these are the bounds. And we want to find integers for which it's a perfect square. And so first, 5 gives us 1, that's a perfect square. 6 gives us 9, that's a perfect square. 19 is not a perfect square, 31 is not, 45 is not, 61 is not, 79 is not, 99 is not, 121 is, so 13 gives us 121. And these two are also not perfect squares. And so the only integers for which p of the integer is a perfect square is 5, 6, and 13. So that gives us three sort of cases here because we want the floor of x to be 5, for example. So then we could have that this thing is a perfect square and it's equal to 1. So there's case 1 where the floor of x equals 5. Case 2 where the floor of x equals 6. Case 3 where the floor of x equals 13. And if we go back to this equation, we have that this would imply that this square root of p of x would equal this p of 5. P of the floor of x is 5, so p of 5 is going to equal 1. This implies p of x, and I forgot the square root, and there's also a floor there. And there's not a floor there. Never mind, I got confused. So we'll erase this. So this would also equal square root of 9, 3. This implies that, well, it's 121. So square root of p of x is going to equal 11. So these are the three cases that we want to solve. And so let's just go case by case, and I'll draw a line here. And first, I think it's helpful to just get a scale or like understanding of what this p of x function is. So before we actually get into the cases, let's draw what this p of x function is, because drawing this is going to help us a lot here. So let's just assume p or x equals 0. And if x equals 0, we get 0 minus 9, so that gives us negative 9. Let's just say that's negative 9. P of 1 is 1 minus 3 is negative 4. So negative 4, or 1 minus 3 is negative 2, and negative 2 minus 9 is negative 11. So we get like some negative 11 down here for p of 1. And then p equals 2. We get 4 minus 6 is negative 2, minus 9 is also negative 11. So we get negative 11, and so this is going to be negative 9, and this is the parabola right here. It's going to look something like so. It's going to look like this. Something like that, where this is 0, this is 1, this is 2, this is 3, and so on. And what's really important is that for 5, 6, and 13, we're always on this side of the parabola right here. And so it's just a strictly increasing function on that side of the parabola. So back to our cases. Let's start with case 1. So case 1 gives us, well, first we want floor of x is equal to 5. That happens when 5 is less than or equal to x, which is less than 6. That's when the floor of x is equal to 5. And then we also have that the floor of the square root of p of x is equal to 1. So floor of the square root of p of x is also equal to 1. Because we got that by plugging it into here. So floor of the square root of p of x is equal to 1. So that means we want the actual square root of p of x to be between 2 and less than or equal to 1. So now if we simplify this, we get 1 less than or equal to p of x less than 4. And we always know that 1 is going to be less than or equal to p of x in this interval because, again, it's a strictly increasing function. And at 5, it's going to, p of x is equal to 1. We know that from here. So at 5, p of x is equal to 1. It's a strictly increasing function, so for any x that's greater than 5, it obviously has to be greater than 1. So if we have p of x, we just need to find p of x less than 4. So let's just solve that. P of x less than 4, x squared minus 3x minus 9 less than 4. X squared minus 3x minus 13 less than 4. So we have to use the quadratic formula for this, and this one is actually less than 0. So, and you can't really factor this, so you have to use a quadratic formula. X equals 3 plus or minus the square root of 9 minus 4 times 1 times negative 13, all divided by 2. And since x has to be positive, since it's an increasing function, we're only working on this side. So we're only going to take the positive root. So we can conclude that x is going to equal 3 plus the square root of 9 plus 52 is 61. All over 2. So this case gives us the inequality that 5 is less than or equal to x, and x has to be less than 3 plus the square root of 61 over 2 in order for this equation to be true right here. So let's box that. And now we'll just go on into case 2. So case 2 is this case right here, x equals 6, and the floor of the square root of p of x equals 3. So if floor of x equals 6, that means we have 6 less than or equal to x, which is less than 7. And we also have that this floor of the square root of p of x is equal to 3. So square root of p of x is between 4 and less than or equal to 3. So now if we undo this, we get 9 less than or equal to p of x, which is less than 16. And again, at 6, we know it's exactly 9. We know that from here. At 6, it's exactly 9. And since it's an increasing function, for all x that's greater than 6, it's obviously going to be greater than 9. So we only have to care about this side. So let's just solve p of x equals 16. So x squared minus 3x minus 9 less than 16, x squared minus 3x minus 25 less than 0. And again, you can't really factor this because you get 5 and 5, so this would be negative 10, but that doesn't work, so we have to use the quadratic equation again. So x equals 3 plus or minus the square root of 9 minus 4 times 1 times negative 25, that's just 100. So it's going to be actually a plus 100. Because it's minus 4 times minus 25, all divided by 2. So x equals 3 plus, we're only taking the positive because we only care about x that's greater than 9, or x that's greater than 6. So it's going to be 3 plus the square root of 109 divided by 2. And so now we have to go in and we have our second thing. We have 6 less than or equal to x less than 3 plus square root of 109 divided by 2. That is the second interval. And now the third and final interval. Third and final interval is this one right here. X equals 13, p of the floor of the square root of p of x equals 11. So if the floor of x equals 13, that means 13 is less than or equal to x, which is less than 14. And we also have that 11 is less than or equal to the square root of p of x, which is less than 12, because the floor of the square root of p of x is 11, so that's what this equation means. And again, we're just going to undo this. 121 less than or equal to p of x less than 144. And again, it's an increasing function on this interval. This is always increasing out here at like 13, 14. It's still an increasing function. So for all x greater than 13, it's trivially going to be greater than 121, because we know that p of 13 equals 121. So now we just want to find p of x less than 144. So now we can just set them equal and again solve. X squared minus 3x minus 9 less than 144. X squared minus 3x minus 153 is less than 0. So now I'll just use the quadratic equation again because you really can't factor this. It has a factor of 9, and then that would be left with 17. Yeah, 9 and 17, but again, 9 and 17 can't get you the difference 3, so we have to use the quadratic equation. So x equals 3 plus or minus the square root of 9 plus 4 times 153. So I'll just write that and I'll save the simplification for later. So x equals 3 plus, again, we're only interested in the positive root. So 4 times 153, that's 400, 200, and then 12. So that's 612 plus 9 is 621 divided by 2. So our third and final interval here is 13 less than or equal to x, which is less than 3 plus the square root of 621 over 2. So now we have 3 intervals, and I'm going to rewrite the first interval down here just so we don't have to scroll up again. So 5 less than or equal to x less than or equal to 3 plus the square root of 61 divided by 2. So these are our 3 intervals. And now we want to find the probability using these 3 intervals. So the probability that our randomly chosen x will be in that interval is equal to this thing. So let's first just find the total interval. The total interval is just 15 minus 5 is 10. So our denominator is going to be 10. And our numerator is going to be the sum of the lengths of these intervals. And so the length of this first interval right here, or this second case, I guess, is 3 plus square root of 109 divided by 2 minus 6. Now this first case, or this one right here, the red one, this interval actually has length 3 plus square root of 61 divided by 2 minus 5. And finally, this last interval right here, this 13 one in magenta, has length 3 plus square root of 621 divided by 2 minus 13. And so this is our gigantic equation that we want to solve. And so now I can just set them equal. I'm going to multiply the top and the bottom by 2. So times 2 times 2. So this gives us 3 plus square root of 109 minus 12. And I'm probably going to run out of room here, so I'll just write it on the next line actually. So this gives us 3 plus square root of 109 minus 12 plus 3 plus square root 61 minus 10 plus 3 plus square root of 621 minus 26, all divided by 20. That's the probability. So we just continue simplifying this. This is equal to square root of 109 plus square root of 61 plus square root of 621. And now we just sum the integers. 3 plus 3 plus 3 is 9. And 9 minus 12 is negative 3, minus 10 is negative 13, minus 26 is negative 39, all divided by 20. This is the probability, and we can see that this is actually exactly in the form of a plus square root b plus square root c minus d over e. So we have 3 square roots minus some integer over e. So 3 square roots minus some integer over e. We want to find the sum, I believe. Yeah, the sum, a plus b plus c plus d plus e. And again, d is the positive part. It's not the negative part because we have a minus d, so we just sum these literal numbers. So we just get 109 plus 61 plus 621 plus 39 plus 20. And so that would equal, well, this simplifies to 170, and I can also simplify this to 190. This simplifies to 660, so 660 plus 190, that's 760 plus 90, which is 850, which is the answer to AIME problem 15.